Okay, recording started. Thank you for letting me know. But yeah, you will need to be able to print out the exam so you can write on it or use a tablet or whatever to write. Either one is fine. Just make sure you have a way to do that. And then instead of 75 minutes, I will give you 90 minutes so you have time to work out the logistics of that. Okay, are there any remaining questions? Okay, if nobody else has any questions, we'll just hop into doing the review. We'll start with today by doing the review, and if anyone has any other questions or problems they want to go over, we can do that as well. Okay, let me share the review. Okay, everyone can see that. Good. Maybe some of you have worked through this. Hopefully, if you can just follow along, check your own work. And if not, just follow along, take notes as you go, and we'll see how we do. Okay, so first question, given a particular circle with a radius r, what does it mean for an angle to be 2 radians? Use illustrations to support your answer. This right here should be the key to your answer. If you recall from when we started talking about radians, I think this was the first day of class, for any particular circle, 1 radian is equivalent to one of those circles' radii. So 1 radian is 1 radius. So before we give our explanation, let's draw a little circle. Just like that. Oops. I didn't give you a number for the radius, but the radius is r, so we can just draw what we know the radius would look like and label it with an r. R could be 5, pi, 20, 72 million, we don't know, but we're just going to refer to it as r just to be general because that's what the problem wants. And so if 1 radian is 1 radius, that means in words that the arc length on the circle between the initial and the terminal side of our angle, so let's draw an angle. That means that arc length there is that of 2 of the circle's radii. So just to write that out, this means that the arc length on that particular circle, of course, between the initial side and the terminal side of the angle, I will call it theta and label that in a second, is just 2 of that circle's radii, i.e. the arc length is 2r. So how would we draw that? We can label this angle as theta. And this is not entirely to scale, but say that's 1r and that's 2r there. That is all it is saying when an angle is 2 radians, because we know a radian is just a radius on the arc of the circle. This just means that the arc length between our initial side, which is usually lined up horizontally like this, and the terminal side of our angle, the arc length on that circle between those 2 sides of the angle is 2 of that circle's radii. So in other words, the arc length is 2r. Any questions on that idea? Okay, let's keep going then. A sector of a circle of radius 5 inches has an area of 13 square inches. Find the central angle of the sector. This one's a lot less thinking and intuitive and thinking about definitions. This is much more computational. If you remember from when we looked at, okay, if we want the full area of the circle, how many radians is that? If we want the area of half of a circle, how many radians is that? We came up with the formula that the area of any sector of a circle is the angle theta in radians over 2 times the radius squared, which just stems from the formula for the area of a circle, which is pi r squared, because that pi, where that pi is, we know that that's a full circle. So the first full circle is 2 pi radians. So we just recognize that, hey, we can just take whatever our angle is and divide it by 2 and then get the area of any sector in general. So we have the radius and we have the area. That means we have to solve for theta here, which we can do just by substituting these values in. So 13 inches squared is equal to, we don't know what theta is, over 2 times 5 inches squared. And then just squaring that on that side, we get 13 inches squared equals theta over 2 times 25 square inches. And before you do these problems, it's always good to check, do the units in our radius and our area match? Because if we had 1 in meters and 1 in inches, we wouldn't get an answer that made sense, because we're going to need these units of inches to cancel. So it's always a good check to check your units before you do this. Okay, now that we have this, we know that we can divide, well, we know that just rearranging things a little bit, 13 inches squared is equal to 25 inches squared over 2 times theta. And then dividing both sides by 25 over 2, which is just 12.5. Plugging this into our calculator, we get that theta is 1.04. And recall that theta is in radians, so we don't need to put any other unit at the end of that, and that is just our answer. Questions on this? Okay. Let's look at number 3. Suppose we have this point x comma negative root 19 over 5, and it's a point in quadrant 3. We want to solve for x. Okay, let's start by drawing a picture. Since we're talking about quadrants, we know we're going to need a set of axes. Here's quadrant 1, here's 2, 3, 4. Okay, so we know our point is on the unit circle, so I'll draw my little unit circle here. And we know the point lies on it. It's somewhere in quadrant 3. We don't know where it is, but it doesn't really matter for our picture. And we know that it's some x value, comma, negative square root of 19 over 5. Okay, what can we do with this? Well, we know the y coordinate. We know that this distance here is square root of 19 over 5. And we also happen to know that that distance there, because we are on the unit circle, that is the key piece of information here, is the unit circle. We know that this length here is 1. We just know that the hypotenuse of this triangle is 1. So taking this image and just transferring it over so it's a little bit nicer to look at, we know we're looking at this triangle. We don't know how far over we're going in the x direction. We do know that this side here has the length of square root of 19 over 5. And the y coordinate is a negative square root of 19 over 5, but just for sake of how we're going to solve it, we can label it like that. And we know we have a hypotenuse of 1. Okay, we have a right triangle with 2 known sides. That means we can apply the Pythagorean theorem, just a squared plus b squared, the 2 smaller sides is equal to the hypotenuse squared. So we don't know what x is, so we'll leave x squared alone, that's our unknown. And then plus, we need to take square root of 19 over 5 squared equals our radius squared, so just 1 squared. Squaring both of those things, we get x squared plus 19 over 25, just squaring the numerator and the denominator, equals 1. Subtracting 19 over 25 from both sides to get the x squared by itself, we get that x squared is equal to 6 over 25, and taking the square root, we know that x is equal to plus or minus the square root of 6 over 5. And that just came from the square root of 6 over 25 is equal to the square root of 6 over the square root of 25, and the square root of 25 is 5. Okay, so we now know that our x value is either positive or negative square root of 6 over 5, but which is it? That information comes from knowing that our point is in quadrant 3, and all points in quadrant 3 have a negative x value because they're on this side of the x-axis. So we get that x is equal to negative square root of 6 over 5, and that is our final answer. Questions on this? Okay, we'll move on to the next question. Okay, we want an equation of the form y equals a sine bx or y equals a cosine bx to describe the graph below. Just from this information here right off the bat, we know we're not working with any vertical shift, but more importantly, we know we're not working with any kind of phase shift, meaning that the start of our box that we usually draw, the start of where the period is on the y-axis. We know that because we know we're not shifting it left or right at all. So that right away tells us that, okay, here we cycle through like that, and then this is where it ends. And just looking at that right off the bat, we can see that it is the shape of a sine wave, because a sine wave is going to start on the x-axis when it has no vertical shift. A sine wave will always start on the x-axis. So that is what happened here. Cosine would have looked something like this or like this, depending on if it was positive or negative cosine. But what we have is the general shape of a sine wave. So we know our final answer is going to be of the form y equals a sine of bx. Cool. Parent graph identified. That's half the battle. Now let's look at what the amplitude would be. We know we have no vertical shift, so the midline will be right here. So our amplitude is just the distance from any of the peaks or troughs, i.e. any of the local minima or maxima from our midline. So we go up here. This right here is at 4, or y equals 4. So we know our amplitude is 4. But what is our a value? Well, is this the negative? Does that look like the negative shape of our parentive sign? Is it flipped upside down, or is it just our normal shape for the parentive sign? Well, the normal parentive sign, if this is our axis, looks something like this, if you recall. So this shape right here in our box is the negative parentive sign. So that means that a, the value that will go out in front right here, is equal to -4. Okay, now all we have to do is solve for b. And if you remember, we have this equation about if we know the period, we know that it's equal to 2 pi over b. So if we can identify the period, then we're golden. We can solve for b. Well, how do we identify the period? We look at how long on the x-axis it takes for one cycle of the sine wave to happen. That is what the period is. And the other way to say that is it is the x bounds of our box. It is the width of on the x part of our box. So we can see that one full cycle of sine goes from 0 to 8 pi over 3. Therefore, our period is just 8 pi over 3, because that's how long it took to get from point A to point B. That's how long it took for one full cycle of the sine wave to occur. And using that formula, we get the 8 pi over 3 is 2 pi over b. Doing some cross multiplication like so, we get that 8 pi b is equal to 6 pi. Dividing both sides by 8 pi, we get that b is equal to 6 pi over 8 pi, which canceling the pi's and reducing our fraction is just 3 over 4. Cool. Now just plugging in our values for a and b into our general form of the equation here, we get that y is equal to -4 times the sine of 3/4 x. And that is our final answer. Any questions? Cool. Okay, then we will move on to the next one, which deals with angular and linear speed. Okay, suppose we know that the planet Mercury rotates on its axis once every 59 days. It makes a full revolution once every 59 days. The equator lies on a circle with radius of 1,516 miles. We want to find the angular speed of a point on the equator in radians per year. Okay, so we have formulas for this. We want something in radians per year. So we know to find that, we call that value omega, just a fancy curly W. It's equal to theta over t, where theta will be our angle in radians, and t is just the time. But in this case, in particular, we want the time in years. Okay, let's see if we can set this up. So we know that Mercury makes one full revolution on its axis every 59 days. So that thing we're given here, I'm just going to write it up here. We know that there's one revolution that occurs every 59 days. However, we don't want things in revolutions. We want things in radians. And if you recall, because there are 2 pi radians in a full circle, one revolution is just equivalent to 2 pi radians. So we can replace this value here, one revolution, with 2 pi radians. So omega is equal to 2 pi radians, i.e. one full revolution every 59 days. This is an angular speed. It is radians over some factor, some unit of time. However, we want it in radians per year, not radians per day. So how do we do that? Well, we need to get these units of days to cancel in order to leave us with years. So I want days to cancel, so I need a unit of days in the numerator with relation to years. Well, I happen to know that there's 365 days in 1 year. So that would make our units of days cancel and leave us with radians per year, which is exactly what we want. So that gives us a fraction of 2 pi times 365 radians per 59 years, which when you plug that into your calculator, do 2 pi times 365 divided by 59, we get that this is approximately 38.870 radians per year. And that is your final answer. Notice that we did not even need the radius for this, and that is because angular speed does not concern the radius. If we think about angular speed, we're just thinking about how quickly rotations happen. But if we're thinking about linear speed, that's when we want to think about distance and how far points are traveling. Angular speed is just how often do rotations happen? How often in whatever unit of time we're given do rotations happen? Whereas linear speed is okay. We know how often these rotations happen. Cool, that's necessary information. But now given that, how far do certain points travel? And that is what part B focuses on. We want to find the linear speed of a point on the equator in miles per year. So if you remember, we also have a handy dandy formula for this one. And that is just V, we call it the V for velocity, is equal to the radius times omega, our linear speed. So we still need that linear speed. We still need to know how many times per year that we are rotating around. However, we now want to know, okay, we need this relationship between the size of the circle we're thinking about rotating and how many times it's rotating around, because we want distance. And that makes sense because we want miles per year. We're not just talking about time anymore. We want miles per year, which does in fact concern the size of the radius because that changes the size of the circumference, et cetera, et cetera. Okay, so our radius as given in the problem is 1,516 miles. And we know that we want this linear speed in miles per year. So cool, we don't even need to do any conversion with the radius. We can just plug it into our handy dandy formula right here and we're good to go. So we get that V is equal to 1,516 miles times, I could use this value here. However, I just want to be as exact as possible just to eliminate any round off errors. So I'm just going to use the exact ratio here, which is 2 pi times 365 radians per 59 years. When we do that math, we'll just get something in miles per year, which is exactly what we want. And when we plug that into our calculator, we get that it is about 58,927.758 miles per year. Any questions on angular or linear speed? The key to these is A, these two formulas, the one for angular speed here, and then using that to be able to find your linear speed, and then making sure your units are kept straight. Are my units what I want them to be? Am I talking about revolutions or radius or radians? If I need my time in years, is it in years to begin with? How would I convert it to years? And a lot of time it's just simple conversion factors like this one that we just know already. Okay, cool. Let's move on to the next one then. So a buoy floating in the ocean is bobbing in a simple harmonic motion. And if you remember, simple harmonic motion just refers, it's a fancy physics way to refer to, it's just a wave, it's just going up and down. With amplitude 6 feet and period 5 seconds. Its displacement d from sea level at t equals 0 seconds is -6 feet, and initially it moves upward. Give the equation modeling the displacement as a function of time. Okay, that's a lot of information all at once. Let's sort it out. Let's draw a picture. So we have some water here, some very poorly drawn water. And here's a buoy. It's just doing its thing in the water. Okay, let's give a baseline here. Let's set up what we're going to call height 0. That's right here. Because we know we're starting -6 feet. So this is 0 feet right here. And so at time 0, we're starting at -6 feet. And then we know we're bobbing up and down with an amplitude of 6 feet. So because we're starting at -6 feet, we know that that is the bottom peak of our amplitude. So we know we're not going to go any lower. So we know that because we're starting at -6 feet, the only thing we can do is go up, then back down, and then back up, etc. Just forever like that. Okay. So first, what does this, we want to model to the displacement, and that is what this wave is. This wave is showing over time how the buoy goes up and down and up and down. So we know our equation is going to be d equals some kind of wave. Just from looking at this right away, what parent does that resemble more? Does that look like a sine wave or a cosine wave? Well, like we've talked about, we can write them as either given a different phase shift, but we don't want to make our lives harder on ourselves because why would we do that? So looking at t equals 0, we're starting not on the x-axis or not at 0 displacement. We're starting with -6 and then we're going up and going down. So if you look kind of at this block here, it is upside down, so we probably will have a negative in the front, but it resembles the shape of the parent graph of cosine, or that principal interval for the parent graph of cosine. So we know we're going to have d, our displacement equals some amplitude times the cosine of something times t plus something plus something. And we just want to figure out what these values for what normally would be a, b, c, and d are. Okay, I'm just going to start with the vertical shift because there isn't one. We're considering 0 feet to be here just by construction of the problem. We're starting at -6 feet, then we're going up 6 feet, and then we're going back down 6 feet below this, above and below the 0 feet line, which means our amplitude is 6 because it's given in the problem. However, because we're starting at -6 feet and not +6 feet, we know we're going to need to slap a negative in front of it, in front of the equation, because it's the negative version of that cosine parent. So we have that this is -6 here, but we also have that the vertical shift is 0 just by construction of the problem, given that we're talking about going -6 and +6 feet above a midline. That is just by construction of the problem. Okay, now let's look at some stuff inside of the argument. Notice right away that we have no phase shift. Why is that? Because we're starting at t equals 0 seconds at our amplitude. We are -6 feet below our midline, and we're given that our amplitude is 6 feet. We know we can't go any lower, and we know that we just know that we're at the minimum, we're at a local minimum right here, which is how the cosine graph or the negative cosine graph starts. So we're not shifted over to the left at all. We're not shifted over to the right at all. There is no phase shift. And what value does that correlate to, or what value does that relate to? That means that C is 0. Because the formula for phase shift is -C over B. And so the only way for there to be no phase shift is for C to be 0. Okay, now finally, let's think about the period. or how we're going to solve for this guy here. We know that we're actually given this information. We're given that we have an amplitude of 6 feet and period of 5 seconds. So we know that our period is just 5, which we also know to be equal to 2 pi over b, if we're considering this value here to be b. So let's solve for b. This means that 5b is equal to 2 pi, and dividing both sides by 5, b is 2 pi fifths. So knowing that, oopsies, we can just plug in 2 pi fifths right here. And that's our final answer. Just writing this a little bit cleaner, the displacement can be modeled by -6 times the cosine of 2 pi fifths t. And that is our answer. The key to these problems is just they look like a lot of information at once, especially when it's talking about things like displacement and modeling real world situations. However, if we can just pick it apart, do even something like this, just thinking about, okay, what does it mean if it starts at -6 seconds and is bobbing up and down? What is that wave going to look like? How can I sketch that? Okay, does that look like sine or cosine, or does that look like something else? So the key to these is just being able to pull them apart and knowing how to use the information you're given. Any questions? Cool. And the key pieces of information to pull out there are things when you're given numbers like t equals 0 seconds, when you're given, if you see the word amplitude and period, that should immediately raise flags in your brain as well. Okay. If there's no questions, we can move on to the next one. This is just talking about finding the exact values of trig functions, as we'll be using a lot of information from the unit circle, and being sure to draw a picture and show your work to justify your responses. Okay, sine of 17 pi over 4. Well, we know we need to draw a picture here because this looks like something that may be familiar to us. However, 17 pi over 4 is not on the unit circle. So what I want to do is find an angle coterminal with 17 pi over 4 that may or may not be on the unit circle, which would make our lives easier. And there's 2 ways you can go about this. One way is just the very visual way of thinking it through, where we start by so-called walking along the circle until we reach 17 pi fourths, which I like to do in intervals of pi. Because we know, for example, from here to here, that was 4 pi fourths because that was 1 pi. Going around again to back here, we know we've gone 8 pi fourths. We're not there yet. Going around again. Okay, now we're at 12 pi fourths. We're getting closer. Going around again, another 4. We're at 16 pi fourths. So we're so close. We just need to go 1 more pi over 4. So that is what our angle looks like. So it turns out, just from thinking about it and thinking about walking along the circle like that, we're given that 17 pi over 4 is coterminal with pi over 4. If thinking about it that way doesn't work for you, there's also a mathematical way to calculate that, and that is just to keep subtracting, or say we're working with a nasty negative angle, adding multiples of 2 pi to 17 pi over 4. Because if you think about it, all we're doing with coterminal angles is going around extra multiples of 2 pi or getting rid of them until we see where we end up. So we could have found that by subtracting. We have 17 pi over 4. Let's start by just subtracting 1 multiple of 2 pi from it. That gets us to 9 pi over 4. Okay, we're still not there. So we can subtract another 9 pi over 4 minus another multiple of 2 pi. That's just another 2 pi. We get pi over 4. So you can either just think about it as needing to add or subtract multiples of 2 pi until you get something on that unit circle. In other words, an angle between 0 and 2 pi, or you can think about, if you're a more visual learner, just walking along that circle in multiples of pi or pi over 2 or whatever you're comfortable with until you reach the angle. Okay, and so now all we have to do is just remember on our unit circle that the sine of pi over 4, which is equal to the sine of 17 pi over 4 because the angles are coterminal, is the square root of 2/2. And that's your answer. Questions on that? Okay, now let's look at a different one, and this one's in degrees. We want the cotangent of negative 150 degrees. So let's draw a picture. We know negative angles, we have to move in the clockwise direction. And we know that this vertical axis right here is where a negative 90-degree angle would be. And we know that this axis is where a negative 180-degree angle would be. So we know that our angle of negative 150 degrees is going to land somewhere between that. Okay. For this one, I think it may help to think about our reference angle, which is this guy right here. I will label him theta prime, just to think about, because it may be easier to think about what the sine or cosine of that angle is, instead of having to think about negative 150 degrees, which is an angle we're not super comfortable with. So if we know that this line here is 180 degrees, and we know we went around 150, we know that the reference angle would be that full 180-degree rotation like that, minus, we already did 150 of those degrees. So what's left is our reference angle is 30 degrees. Cool. So now that we have that, we can use this information to say that the cotangent of negative 150 degrees is either plus or minus the cotangent of 30. We don't know whether it's the positive or the negative yet. We can think about that once we have the number, but we know it's plus or minus the cotangent of 30 degrees. And if you remember from the unit circle, 30 degrees is a special angle. In radians, it happens to be pi over 6. Whether it's easier for you to think about it in degrees or radians is fine, but you have to be able to recognize either way, hey, this is a special angle. We've used it before. How can I use it now? So we know it's the cotangent of pi over 6. And cotangent, if you remember, is just the inverse of sine. It is the reciprocal, or not the inverse of sine, it's the reciprocal function of tangent. So instead of sine over cosine, it is the cosine of pi over 6 over the sine of pi over 6. Cosine of pi over 6 is just root 3 over 2. Sine of pi over 6 is just 1/2. So doing that division, we get that it's plus or minus root 3. Okay, cool. We know it's one of those two. Beautiful. We're almost done. So now we just have to think about what quadrant we're in. We know we're in quadrant 3, just based on where this angle lies, which means we have a negative x coordinate and a negative y coordinate. And we know that this is cosine of the cosine will be negative because we're in the third quadrant, and cosine is the x value. So, and sine will be negative because we're in the third quadrant, and the y value is negative, and sine is just the y value. So to do cotangent, we know that we're doing a negative divided by a negative, which is always a positive. So our cotangent in this case will be positive. Therefore, our answer is that the cotangent of negative 150 degrees is equal to the positive square root of 3. And that's your answer. Questions on either of these, how we use reference angles in order to solve these, or how we find a coterminal angle in order to solve these? Some work better in certain cases. Go ahead.
Can you go over how you determined whether it was positive or negative again?
Yeah. So if you remember, the cosine always just comes from the x coordinate, and the sine will always just come from the y coordinate. So we know in this case that we have a negative x coordinate because we're in quadrant 3 and all of the x values over here are negative. And we know that we have a negative y coordinate because we're in quadrant 3. And so all of the y values that could possibly be in here are also negative because we're working on this side of the axis. So we know we're going to have we're going to be having negative root 3 over 2 divided by negative 1/2. And we know that a negative number divided by a negative number is a positive number. The cotangent of any angle in quadrant 3 will always be positive because of that. Does that kind of make sense?
Yep, thank you.
Yep. Any other questions on this one? And we'll get some more practice with that analysis of how we know whether things are negative or positive just in a second here. I think it's it's on the next page. Cool. So if there's no other questions, I'll move on to the next one. And this is just a bit more practice with reference angles. I want to find the reference angle for 19 pi over 9. So just by looking at this, this is going to be probably easiest just to walk around the circle to find. We could also do the method where we find a coterminal angle, which I will do that in a second. But just thinking about walking around this, we know we're going to walk in steps of pi, just because that's an easy factor to think about. So I'm going to go around 9 pi ninths. Okay, we're not there yet. 18 pi ninths. Oh, we're almost there. We just have to go up one more pi ninth, and this is our angle. If you remember, the reference angle is just the angle from the terminal ray of our angle to the x-axis, and we know we had to go, this was 18 pi ninths right there. We know we had to go just one more pi ninth above in order to get to our terminal ray of the angle. So the reference angle is just pi ninths. We could have also found that by taking 19 pi ninths and subtracting 2 pi from it, because 18 pi over 9 is just a really fancy way of writing 2 pi's, just making a common denominator, and then it's pi over 9. Those two angles are coterminal. You could have just drawn the angle pi ninths and seen, okay, that reference angle is pi over 9. And once we have that reference angle, we can use it to determine information about the sine, all of the trig ratios of 19 pi ninths. It wouldn't have been as easy or nice in this case because pi ninths is not on the unit circle. However, it is still a good skill to be able to identify a reference angle. Questions on this? Okay, let's do number 9 then. We want to determine the quadrant in which the terminal side of theta lies in these two cases. Case 1 is where the cosecant is positive and the cosine is negative. Before I get into this particular question, I think it's always helpful just to draw a little diagram. And that would be the diagram of, okay, in which quadrant are my y values positive or negative, and in which quadrants are my x values positive or negative. So just going to label my quadrants, just to remember which is which, going around counterclockwise, starting with the positive quadrant. We know that in this quadrant, our x values are going to be positive and our y values are going to be positive. In this quadrant, we're now looking at negative x values, but still positive y values because we are on the positive side of the y's. Like we talked about in the last problem, quadrant 3 is going to be negative because we have negative x value, negative y value. Then quadrant 4, we're back in the positive x values, but we're still in the negative y values. This is pretty much all the information we need to complete this problem. So what am I going to do now? Instead of trying to consider both of these at once, I'm going to look at both scenarios and see where the overlap is. Okay, cosecant is greater than 0. If you recall, cosecant is just the reciprocal function of sine. So what we're looking at here is where the sine is positive, because if the sine were negative, the cosecant would be negative, because sine is just the y values. That's how we figure out if the sine is positive or negative, whether we're in a positive or negative quadrant for y values. So where is cosecant positive? In other words, which quadrants are our y values positive? Quadrant 1 and quadrant 2. So this is true in quadrants 1 and 2. Okay, now let's think about where the cosine is negative. If you recall, cosine is just the x values on the unit circle. As such, whenever our x values are negative, our cosine will be negative. And which quadrants are our x values negative? Quadrant 2 and quadrant 3, because those are the two quadrants where we are working on that side of the x-axis. So this happens in quadrant 2 and quadrant 3. Okay, so in which quadrant do both of these things occur? Well, not quadrant 1, because we have positive x values, and not quadrant 3, because then we have negative sine values. The only quadrant where these two overlap is in quadrant 2. So that is your answer. Questions on that? Okay, let's do one more. We want a positive sine and a positive cotangent. Okay, well, we know that sine is positive in the quadrants where we have positive y values because the sine is just the y value on the unit circle. What quadrants does that happen in? Well, on the quadrants that involve that part of the y-axis, which is quadrant 1 and quadrant 2. Now, when cotangent is positive, if you recall, cotangent is just cosine theta over sine theta, which on the unit circle is just the x over the y. So the only times when cotangent will be positive is when we're dividing a positive by a positive, because that results in a positive, or when we're dividing a negative by a negative, because that will result in a positive. If we're dividing a positive by a negative or a negative by a positive, we will have a negative cotangent. So what does that mean? It means we need to look into the quadrants where the sign, meaning the positive or negative sign of the sine and cosine, are the same. That happens in quadrant 1 because both are positive, and in quadrant 3 because both are negative. So the cotangent is positive in quadrants 1 and 3. Now, where do we have overlap? We have overlap in quadrant 1. Because in quadrant 2, we would have a negative cotangent, so that would violate that. And in quadrant 3, we would have a negative sine, so that would violate that. We want to look at where these are both true. Questions on that? Or that kind of analysis? Okay. There's no questions. We will move on to question 10. In the figure below, we have two similar triangles. We're saying triangle XYZ is similar to triangle BAC. We don't technically know any of the side lengths of BAC, but we want to find the sine, cosine, and tangent of C. The key here is that when we have similar triangles, it means that we will have the same trig ratios. Because if you think about it, sine, cosine, and tangent, the little cheat we use to determine those values, is the acronym SOHCAHTOA, where its sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So even though the side lengths of BAC may be different than XYZ, being similar means that our angle C, our angle B, is equal to angle X, because those are the right angles. Our angle C is equal to our angle Z, and our angle A is equal to angle Y. So even though the side lengths may be different, our angles are congruent. This here is congruent to this, and this is congruent to this. Therefore, we can just use the information from a similar triangle in order to find the trig ratios for the triangle that we don't technically know any of the information about side lengths about, and we never will be able to know, but we'll never need to know. So how do we do this? Well, we just know that the sine of C, that's the first thing we want. We know that it's equal to the sine of Z because those are the two angles that are the same, that are congruent in the similar triangles. We know that the sine from our acronym up here is opposite over hypotenuse. So we want the side opposite of Z, which is 15.4 over the hypotenuse, which is 17. And this says round your answers to the nearest hundredth. You can just plug these in division, these fractions into a calculator. Similarly, if we want the cosine of C, we know that's equal to the cosine of the corresponding angle in the similar triangle, which is Z. And from our acronym, SOHCAHTOA, the cosine is the adjacent side to Z over the hypotenuse. The side adjacent to Z is the side 7.2 over the hypotenuse of 17. Lastly, we want the tangent of C. That's equal to the tangent of corresponding angle Z. And tangent is just opposite over adjacent. The opposite of Z is 15.4, and the side adjacent to Z has length 7.2. And if it says on the exam something like round your answers to the nearest hundredth, you can always just plug that into a calculator and do that. Questions here? Okay, I think we have 2 more. So let's work on these. Okay, this is what we've been doing a lot of lately. We're going to get one practice problem with it. And this is what basically your entire homework is practicing. So it would be really good review to do that, but I put another one on here just for further review. We want to graph the function y equals 3 times the cosine of 2x minus pi plus 1. Okay, so let's just follow our steps. Let's follow the little step-by-step guide we've created to make this easier for ourselves. First, this seems like the most trivial step, but we want to identify the parent and that we will be transforming in the box we create. Here, the parent is the cosine of x because cosine. Second, we want to look at amplitude and vertical shift. Amplitude, we just pluck the coefficient, the multiplicative coefficient off the front of the trig function. So our amplitude is 3. And amplitude is 3. And then vertical shift, we just look at if there's any constant added or subtracted from the end of the equation. And we see we have a +1 here, so we do have a vertical shift of 1. This information gives us enough to draw what the y bounds of our box will be. We know that our midline is 1 because we have a vertical shift of 1. So we know that right here is going to be our midline. And because our amplitude is 3, we know we need to go 3 above it and 3 below it. Cool. Questions there? All right. Now let's look at the other part, which is identifying the phase shift in the period and using those to figure out what the x bounds of our box will look like. So we don't actually need to identify them, but this will give them to us. Because we're working with cosine as our parent, we know that the principal interval for cosine is between 0 and 2 pi. So we want to solve for what bounds our principal interval is going to be with this inequality between 0 and 2 pi. Adding pi to both sides, we get that pi is less than or equal to 2x is less than or equal to 3 pi. Then dividing both sides by, well, all 3 sides by 2 in order to get x by itself, we get that we're going from pi halves to 3 pi halves. So what does this mean? This means the x bounds of our box are going to be from pi halves to 3 pi halves. So I've actually made us a pretty narrow scale here. The scale on the exam will not be this bad, but this is where our principal interval is going to be. Now we can sketch what the cosine wave will look in this box, because we know the cosine wave of the parent looks like this. So we know we're going to have 2 points up here, 1 point down here, and then 1/4 and 3/4 of the way through the points on the midline. This was a horrible scale. I am so sorry. And as a result, I may not draw the entire thing, but just from that, we can kind of see what it's going to look like. And actually, let me, hold on, can I fix the scale? Yeah, I'm just going to divide the scale by 2 over here. So this right here is actually pi instead of being 2 pi. So I can spread it out a little bit. So that would mean we're going from pi over 2 right here to 3 pi over 2, which would be right here. That makes it a little bit nicer, not entirely nicer, and I apologize. But we know that that's going to be the same. If we just stretch it out a bit, we're going to have a cosine wave that looks something like that. Again, I'm sorry about this. I will give you a much nicer scale for the graph on the exam, I promise. But it's going to look something like, oopsies. It's going to look something like that. I want you to draw it much nicer on the exam. And again, I will give you a scale that allows for that. I didn't realize how bad the phase shift made the scale when I made the review, but the same idea stands. When you do your final graph, I will probably ask you to, if there are asymptotes, to graph those. There are not, so you don't need to worry about this time. But if there aren't asymptotes, if it's something like a sine or cosine wave, just plot one of these points. So this one would be pi over 2, 4. And down here would be pi negative 2, just to give one minima and one maximum point. So if I say plot a point of a minimum, a local minimum and a local maximum, that is what I'm referring to, is just writing, oopsies, writing an ordered pair like this. Any questions on graphing? You will always be given two sets of axes if you're asked to graph something. And that is because a very large portion of what you will be tested on is whether or not you can draw this box and go through this analysis here to figure out what pieces you need to draw the box. Okay, so if there's no questions, let's move on to our final problem. So let's say we have an angle theta at 2 pi thirds. And if you remember, this is about what 2 pi thirds looks like. And I want to find the exact value of each of the following expressions. First is just 2 times the sine of theta. If you remember, the 2 out in front just means we find the sine of theta and then multiply it by 2. From the unit circle, if you remember, 2 pi thirds is one of our special values, and the sine of 2 pi thirds happens to be the square root of 3 over 2. So this is just 2 times the square root of 3 over 2, which is just square root of 3. Okay, what about sine of theta over 2? Well, the sine of 2 pi thirds divided by 2. We need to evaluate this expression before we evaluate the sine because it is inside the argument. So we are just instead dividing that by 2, looking for the sine of pi thirds, which is also a special angle on the unit circle, luckily enough, which also happens to be root 3 over 2. Lastly, we want the sine squared of theta. If you remember, sine squared of 2 pi thirds, even though it kind of looks like it's inside the sine argument, it's not. It's just asking us for the sine of 2 pi thirds, quantity squared. So we do want to find the sine of 2 pi thirds first. As we discussed in part A, the sine of 2 pi thirds is just root 3 over 2 squared. We square fractions by squaring the numerator and the denominator. Root 3 squared is just 3, 2 squared is 4. Questions on these? Okay, so that is it for the review. This is about the length you can expect for the exam when it comes out. So if you could do this in 75 minutes, you're golden. If this was not enough review for you, if you want more practice, I highly, highly suggest looking at ALEKS. Tomorrow, your second chance exam 1 topics will reopen, so that will be a resource for you to use. And I believe you can always go back into topics you've already learned and just try more practice problems. So if there are any topics in particular you are struggling with, I highly recommend looking at ALEKS, especially because ALEKS walks you through the problems. You can ask it for the solution. So that is a good resource. Your notes are a good resource. There's the recorded lectures. I would even, if you're struggling, if you know a classmate, email a classmate. I know it's harder because we are online, but you are good resources for each other to study as well. On that note, are there any other questions or things people would like to go over?
I had a question on problem number 6 on the homework, the written homework.
Yeah, written homework number 2.
Yes.
Okay, what was your question on that? Let me see if I can pull that up.
Based off of
Go ahead.
the
Sorry, that's the wrong one. Okay, so question 6.
yes. So do we need to have is the -1 is that a vertical shift or is that still going to be part of our phase shift?
Thank you for asking. That is called a typo. Oopsies. This should actually be y equals negative secant of 2x plus pi over 2 with the -1 outside of the parentheses. So it will be a vertical shift. Thank you for
All right.
noticing that. I
Yep.
didn't realize that is a typo, and I will put out an announcement after class clarifying that the -1 should be outside of the parentheses. It is a vertical shift. Thank you.
All right, thank you.
Any other questions?
I had a question over the same problem, actually. I guess everybody's I'm struggling with the graphing the secant and the cosecant.
Yeah, is there any particular part you're struggling on, or is it just how to get started with the problem?
Yeah, mostly how to get started with it,
Okay,
like how to set it up.
okay. Well, let me go to the notes for the secant, and then we can talk through it that way. Okay. So do you remember what the problem was? I forgot what it is. It's y equals, come on, there we go. Y equals negative secant of 2x plus pi over 2 minus 1. So maybe I'll be able to use these axes to help a little bit, this little extra third set I have. So the first step with secant and cosecant is always just recognizing what function is it a reciprocal of. So secant is 1 over cosine. So the first step is always just going to be slapping a cosine in where the secant was and graphing that. So instead of trying to think about secant at first, all we want to do is think about negative cosine of 2x plus pi over 2 minus 1. That's what we want to think about. That's the first step. We don't want to mess with secants at first. We just want to look at the cosine graph. Just looking at this right away, I can see that the amplitude is 1 because there's no multiple out in front. And then cosine's period is 0 to 2 pi. So we're going to want to solve this inequality in order to get the x bounds of our cosine box. Doing that, we get negative pi over 2 2x to 3 pi over 2. And then dividing both sides by 2, we get negative pi over 4x 3 pi over 4. So the x bounds of our box would be here and here. So that is the box for the cosine graph. So we now have enough information. We know it's the inverse of our cosine graph to just sketch what the cosine curve would look like. It will look something like this. And we actually want to extend this to the rest of our graph. Cool. Oops, a little better. And now the key to finding what the secant graph looks like. Oh, sorry, there's a question. Katie, I'll answer your question more in a sec, but the exam will be written. There will be no Alex portion. And I'll talk about that more again at the end. But the key to converting this cosine graph into a secant graph is recognizing that at the zeros of the cosine graph, the secant graph, in other words, the graph of the reciprocal function, will have asymptotes. So every time this cosine function is 0, we will have x asymptotes on the secant graph. So I can just sketch those in now. Like that. And the other key point is that at the peaks and troughs, i.e. the local minima or local maximums of the cosine graph, that is where we're going to have these little paraboloid shapes come down, touch, and go back up. So I don't have another set of axes to demonstrate this on, but all your final graph will be is these asymptotes labeled with what they are. So this one's like x is negative pi, X is negative pi over 2, etc. You'll label your asymptotes, and then it's just making sure that these points are at the correct point and drawing them between the asymptotes like so. If it's at a local maximum like this, the U will go upwards. And if it's at a local minimum like that one down here, the U will go downwards. The domain extends from negative infinity to infinity, or the range does. And the domain is also negative infinity to infinity, but just without those asymptotes. Does that kind of make more sense?
Yeah, I think that helps for sure. Thank you.
Yeah, if you can just draw, if you can take, oopsies, why is the eraser on? If you can take this and just say, okay, what's my reciprocal function? And then just graph the reciprocal function, graph that sine or cosine wave, whatever it looks like, that's half the battle.
And then for the cosecant, do you just do that with the reciprocal cosine, the reciprocal of sine? Then is that
Beautiful, yes, because
Okay.
the reciprocal of secant is just 1 over cosine. That's why we use cosine here. So when we're working with graphs of cosecant, we're going to substitute the reciprocal function of cosecant, which is sine, because cosecant is just 1 over sine theta. And it feels backwards because I want cosecant to be the reciprocal of cosine because it just sounds nicer. But if you can remember these two things, and then if you're able to graph sines and cosines, you're pretty much already there to being able to graph secants and cosecants. Any questions on this? Any more questions? Okay, are there any other topics or questions anyone wants to go over? Okay. If not, then I'll just go over the logistics for the exam one more time because I know I was not recording the first time. The exam will be completely written per the question I just received. There will be no ALEKS portion. I know in the past in college algebra, half of the exams were taken on ALEKS. There is none of that for this. It is just a 75-minute written exam. Normally that would be taken in a 75-minute class period. So as a result, I will give you 90 minutes to take it. So you have that extra 15 minutes to be able to print it off, get it uploaded to your iPad, whatever you need to do, just so you're able to write on that. If you have any problems with submitting it, let me know. I'll be checking my email all day tomorrow. There will be no class because we did review today. And then next Monday is when we will start jumping into trigonometric identities, which is unit 2. Make sure that you get the ALEKS module for other trig graphs of other trig functions. That is due tonight. And then tomorrow, second chance ALEKS topics opens. And what that is that if you missed any topics from unit 1 at all, so starting with the angles and radians that we did the first day of class through now, if you didn't do them for some reason, you have the chance to go back in and learn those topics for full credit. So say you didn't do anything all semester and you just completely, something happened, you just didn't do anything, you can still get full ALEKS credit, but you have to go into second chance topics and do those topics over the weekend for that. That opens tonight at midnight, and then you have through the weekend to do that. It's also really good if you want to do some of it Friday morning before you take the exam. Again, I think ALEKS is a great tool to use for review. You also have your third knowledge check this weekend. Again, do your best on those. You will just get participation points for doing them. But I always suggest that you do your best because that is how you master topics, and that is half of your ALEKS grade at the end of the semester. You get points for having your topics learned on time, and you also get points for what mastery you retain by the end of the semester. And the better you do on these knowledge checks, the better that score will be. Okay. Any final questions? Okay. Well, if anyone has any, I will stick around for a bit. Otherwise, there will be an assignment for called exam 1 that I will put up, and then we'll open tonight at midnight Mountain Time, and then you'll have 24 hours to do the exam. And I will check my email tomorrow in case anyone has any questions. But otherwise, I hope you have a wonderful rest of your Thursday and a wonderful weekend. And I will see you all in class on Monday.